Okay, guys. Let's look at these real quick. Hydroboration, oxidation. We're going to do a sit. Well, there's really no stereochemistry here. We'll have to learn when stereochemistry is important. But I got to that point. And I know the magic step replaces the boron with an OH. And there's your final product. 5-member ring CH2OH. How we do? Good. Oxymercuration followed by reduction with sodium borohydride. Basically, you also have a little bit of prompting memorization. You know that's hydration with Markovnikov. And so you're going to get the OH on the more substituted carbon. You can think mechanistically. You get the mercuronium ion, water attacks the more substituted. You open that up. That leads to the structure in the middle. Sodium borohydride replaces the mercury with an H, and there you go at the end. Iodine monochloride. The iodine is partial plus. Pi electrons attack that. Back bonding. I'm not showing full mechanism. I'm just kind of doing it in my, shorthand. Doing it enough that I can show an iodonium ion. Chlorine attacks at the lower carbon, opens that up. Importantly, though, it attacks backside. So the iodine and the chlorine are going to be opposite. This one here, iodine, chlorine opposite, and chlorine attacks here. Because more likely to have partial plus on that carbon because that's where the methyl is donating. It's the same place you'd have a carbocation, but it's not a free carbocation because the iodine is back bonding. That's why you get the trans and the two halogens at the end. How'd we do on that one? Good. Yes. Starting material that would give that product the best yield would be the first one. Choices there. You have, you're going to make cation on top or bottom. Top be a tertiary, and that's where the bromine is there on the end. Bromine attacks there. See this guy where you're going to make cation, left or right? It's not going to be selective. It's going to be either side. So you're going to get that, but you're also going to get some bromine over here. Which one are you going to get? They're both the same. You're going to get tertiary either way. So it's not going to be selective. Here. Well, you're going to get it here. The only way to get that product is if the tertiary rearranged to a tertiary. Well, the tertiary is probably not going to rearrange to a tertiary. First one, how we do? Question?
Yeah, I have a question. So this is actually like 1AB. So when you write OH, you didn't draw the bond between the O and the H. Can we do we have to show that? You know what I mean? For hydroxyl or alcohol.
The OH?
Yeah. Or do we have to show O bond to the H?
Yeah.
It's kind of a shorthand versus literally the bonding.
No, I mean I really didn't ask for full Lewis structure. I didn't put lone pairs on my oxygen.
Okay.
That's typically how you'll see things drawn unless you're asked to be very specific. Which one is not stereogenic? It would be this one here. There's no E or Z, right? I mean, this here you could have. Is this E or Z?
Z.
It's the same size.
Yeah, that's Z.
Same size.
It's the same size. Okay? You can also have E. Basically, the methyls are trans here. You can also have a compound where the methyls are cis. I mean, this is trans here. With two substituents, you don't even need EZ. You can also have these groups cis. Same thing here. Well, here cis trans doesn't work. Is this E or Z?
E.
That's E. Your alpha group is going to be larger. They're opposite. That's E. You can also have Z. The two alphas could be on the same side. Here, you can't have anything. I mean, if you put the methyl up, it'd be the same thing. It'd be the same compound, just flipped over. If you try to do E or Z, you can't do it. Okay, mechanism. All right, I suspect this is your first quiz of ever mechanisms. Okay, won't be your last. Okay. How do you go from here to there using these reagents? Using appropriate arrows. Appropriate arrows. Okay. Show all electron movement. Detailed stepwise mechanism. It's okay to show that ionized alkene attacks H+. Electrons move out, we get carbocation. We're going to have an alkyl shift. Methyl moves over. What this is here, get this cation. We need this cation. That's how the methanol is going to add there. Electrons for methanol add here. That gives a bond between oxygen and carbon. There's only one lone pair on the oxygen. That's a plus charge. We have not magically lost the H or the methyl. How do we get to the final product? We then lose the H. We can have bisulfate take the H. Electrons move on to oxygen. That's how there's two lone pairs there. Or you could use methanol to take the H, or water. I mean, sulfuric acid is an aqueous acid. Something's got to take the H, leave the electrons behind. So basically there was an alkyl shift here from a secondary carbocation to a more stable tertiary. How we do? When you get your quiz back and it says WDAM, WDAM, that means what does arrow mean? Okay, if you don't use the arrows correctly, I'll say WDAM. You probably already got that on the lab report. Yes, question.
So on that last step where you have H support taking that hydrogen, if I just have the H coming off of the oxygen, is that enough?
I don't know what you have, but that's what you should have right there. I don't know any other way to show it.
As in I just don't have the H support.
What took the H?
No.
Something takes it, right? Something's got to take it. Okay, this will be posted on third floor in the glass case. If you didn't get your lab report back yesterday, stop by after class. No lab reports due this week. That was the bromination lab. Doing polarimetry in lab. It went pretty well yesterday. Polarimetry of naproxen, Walmart brand naproxen. We'll start stereochemistry today. I'll address this again on Thursday, but I think the bromination lab report is going to be due in here on Tuesday, except for Monday lab. Monday lab you'll turn in on Monday. Everybody else will turn in here Tuesday. Everybody else. Okay. What will be consistent among you all is a question. Yeah, I need to address that because next Friday is we're off, and so it throws a kink in the whole week. Going to have to address that on Thursday.
So would we have one next week?
Oh my God.
There is something listed on the lab for next week, okay? The lab schedule. Friday's group is not required to be here on Friday. Friday is a day off. We need to finish up the hydrogenation of alkenes to alkanes. Hydrogenation, also known as reduction. Whenever you add H's, that's reduction. Precious metal catalyst, which is palladium or nickel. The H's add in what type of manner? Syn, or the same side. They came from, okay, they come from the same side. So if you reduce this compound or hydrogenate, you're going to get the cis alkene only. The two groups are cis because the two H's are cis. But I don't think it says here. You would also get an enantiomer of that compound. enantiomer is where everything's reversed. As long as we keep the backbone the same, and so we draw this here dashed and this here dashed. So thus the H's are forward here. The H's are forward if both H's come in from the front. They come in from the front, they're forward, it pushes both groups back. Okay? But the two H's could also come in from behind the wall. See, that's a planar, both of these carbons are planar. The alkene's a planar system. H's come from the front, you get this. If the H's come from the back, you get this. They come in from the back, they push the existing groups forward. Okay? But it's a 50-50, because it's just as likely to come from front or back. That's the mirror image, that's the enantiomer. We'll learn about that. What's it say down there? Which is more exothermic? More exothermic is basically where we ended. Do you expect hydrogenation to be exothermic?
Yes.
Well, based on this, yes. Why? Here we got a pi bond. What are we making new? Okay, we're breaking what? A pi bond, what are we making? Two sigma bonds. Okay, they're different atoms, but we're breaking a pi bond, we're making stronger bonds. Okay, if you did a calculation, would it be exothermic or endothermic? Probably. It'd be exothermic. Okay? The bond you're breaking is weaker than the two you're forming. Which would be more exothermic? Did we answer this last time? They're both going to the same place. If we plotted this with a reaction coordinate diagram, just very brief, I'm not even going to label anything, we know where we get here. The alkene, well hold on, let's put the alkane. The alkane is the same, let's just put it here. Boom, 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 boom. Different starting materials. Is there a difference between these in terms of their energy? Their isomers. Is one, which one is lower in energy? That one's lower in energy. Why? It's more substituted. We talked about that. This is a disubstituted alkene. That's a monosubstituted. So if we call this one A and this one B, these are both higher than that one because they have pi bond. We put one here, one here. Which one's lower? A? B? All right. How many intermediates in this mechanism? There's really no intermediate. Just the H's are added. There's no carbocation intermediate or anything that we showed up there. We just got a transition state. Basically, boom. This one goes boom. Basically, exothermic is just the difference right here, yeah? So this one goes from here to here. This one goes from here to here. Which one gives off more energy?
B.
B. I mean, it gives off that much energy compared to A. Why did B give off more energy? Does it contain more energy to begin with? It was higher energy to begin with. So that would be more exothermic. Does that make sense? It's a very simplistic look at where we're starting with. They're both going to the same place. B starts higher in energy. On the flip side, this kind of table or graph here shows pretty much the same thing. It shows three different alkenes. All right, it's not line bond. All right, you got to get used to looking at structures many ways. They kind of got it in there, and then they show the double bond there. When you reduce these double bonds, they all become that. They all become the same thing, but they start at different places. This is a monosubstituted alkene. That's a disubstituted. It's tri-substituted. Tri-substituted, it sits lower. Since it sits lower, it gives off less energy when it comes to this spot. It's the same idea that we just showed on the previous page. The heat that's given off when you hydrogenate is called heat of hydrogenation. So back over here, B gives off more heat, so we say that B, the reaction of hydrogenating B, has a higher heat of hydrogenation. Heat of hydrogenation is not a delta H. If you quoted delta H, you would say that this reaction B had actually since it's exothermic, delta H is negative. So you got to be careful. It's a larger negative number. It's actually a lower. You get confused, I do. Whenever you quote a heat of hydrogenation, it's the absolute heat that's given off. More heat given off, higher the heat of hydrogenation. More heat given off here. Same thing here. Which has a higher heat of hydrogenation, left or right? Right. What's the difference? They're both disubstituted alkenes.
One is cis, one is trans.
Is one more stable than the other?
Yeah.
Trans is more stable. With alkenes, trans is more stable. Just like with alkanes when we did rotation in like Newman conformations. Trans or anti more stable. This guy's just stuck in the good conformation. It can't rotate. That's stuck in the bad one. This is higher energy. When you hydrogenate these, what do you form? What's the name of the molecule that's formed when you hydrogenate it? Specifically. Butane. Yeah. You hydrogenate either one of these, you get butane. Same thing. But this is going to give off more energy in that reaction. We'll have a higher heat of hydrogenation because it has higher energy to begin with. Because it's sitting in that high energy conformation. Well, careful, don't call it a conformation. These are not conformers. So we've got to be careful about calling that a conformation. That sounds like it can rotate. It can't rotate. While we're on this little topic of sort of asking questions about things, which reacts faster with HBr? Totally different question. I would address this by looking at what type of cation is going to form. If this reacts with HBr, what type of cation you're going to get? Division tertiary carbocation form? Yeah. Tertiary carbocations are easier to form. It's going to react faster. And indeed, it reacts about 100,000 times faster. You measure a rate. Because over here, when this reacts, what type of cation does it form? Either way.
Secondary.
Secondary. The problem is that you're not starting at the same spot. Almost, but not quite. Let's look at one down here. Both of these give the same product, that. At some point, you need to make sure you see that. Both give the same product. Which reaction would be faster? Faster meaning easier. Faster meaning basically lower activation energy. Lower the activation energy, it's going to be easier and thus faster. If you plotted it like this, we're going to the same position. We're going to the same end result. Is there a difference between where it starts? Which one is higher in energy? Top. They're isomers. But the one on top is disubstituted alkene. This one's tri-substituted. It's higher in energy. And so if we said A and B here, this would be B, correct? That's higher in energy. So we could put these relative here. They both give the same product, C. Okay? an intermediate here. What does the intermediate look like? Carbocation. What's the carbocation going to look like here? We're going to make cation on left or right? Right, there it is. We're going to make cation on left or right? Left. And when we make it, what's it going to look like? Same. Both of them give the same cation. So if we put the cation up here, it would be right here. And so this one sort of gives this, and then it falls downhill. This one starts different, but it gives the same thing. This one sort of comes up and sort of becomes that one. It's two different transition states, but they eventually become the same thing. Which one's going to get to this easier? Tell me again? B. Why? Because it's closer to that. If you're climbing a mountain, here's the top of Mount Everest. Who's going to get there quicker? The guy that's here or the guy that's down here? That guy's going to get there quicker because he's already up there some. So which is going to react faster here? This guy here. Okay? Your reaction coordinate diagram, understanding your mechanism helps you work problems like this. See what type of questions come up with that next time. A few miscellaneous things. First off, hydrogenation of alkenes. Where have you heard that for? Partially hydrogenated fats. Okay. Your natural oils have lots of alkenes in them, like olive oil. Problem with olive oil is it doesn't store well. And so businesses don't want to use it because it goes rancid quick. Because the pi bonds react with oxygen. Okay? So what they do is they want to get rid of some of those alkenes, certain alkanes, and then the product will last longer in using it. But they don't want to totally saturate them all or that'll become lard. Okay? So they partially do it. They just give enough hydrogen to partially saturate it. But then you get the what's so-called partially hydrogenated fats. Those aren't good either. The best ones are the ones that have lots of cis alkenes that are not hydrogenated, but they go bad easy. Businesses don't like to use them. But you can use them at home because you don't use as much. You don't have to worry about that. Here's an example of a hydrogenation in making the drug Propecia, used to treat hair loss. It's the same compound that's also used for prostate enlargement. But in the synthesis, there's a hydrogenation right here. This alkene, they're hydrogenating with hydrogen and platinum oxide. Basically, this becomes platinum metal. So there's an example of a hydrogenation. Also, a very important application here. You all have this, right? Print out, yeah? Your body also does reductions that almost look like hydrogenations. Okay? But your body doesn't use hydrogen gas like we do in the lab. It uses other enzymes, reducing enzymes, hydrogenating enzymes. One important reaction is testosterone, this double bond, this alkene right here, gets reduced or hydrogenated to, why is it called dihydrotestosterone? Dihydro? Those two H's have been added, okay? But it's not H2 in platinum, it's an enzyme called 5-alpha reductase. And this molecule here leads to like hair loss, and it leads to prostate enlargement when this starts building up. So how can you keep this from happening? Stop this from happening here. And so if you can inhibit this enzyme, you can decrease the amount of this formed in the body. And so drugs can target this enzyme, and drugs like propecia indeed do that. They target that enzyme and make it so it doesn't work as well. But it's a hydrogenation enzyme right here. There's 2 new H's added. You see lots of hydrogenations in biochem. But again, the body doesn't use hydrogen gas. Okay, we need to get on to stereochemistry. I've got a yellow handout, and then one I sent by email that hopefully you have printed. Chirality, where do we begin? Let's see if we can make a molecule here of oh, there it is. It's up there under that long paragraph. RNS enantiomers of 1-bromo, 1-chloroethane. 1-bromo, 1-chloroethane. That might be it right there. Let's look at the white page first. Several warm-up questions on the white page. Hopefully you've been looking at these, read the chapter, etc. Number of chiral carbons, number of stereoisomers, etc. Look on the back, on the flip page, back of the first page. Basically, the message right here is stereochemistry is very important. For example, what's the difference between cellulose and starch? Well, they're very similar, okay? Polysaccharides. The difference is just stereochemistry. And if you look right here, both of these bonds are equatorial. But in starch, one is axial, one is equatorial. They only differ in their projection, okay? They have the same connectivity, just a difference in how they're projected from that connectivity. Huge difference. Our body can digest starch, but we cannot digest cellulose. Stereochemistry makes a huge difference. If we could digest cellulose, we could eat trees and stuff, and there wouldn't be a problem with food. All right? That's just stereochemistry. We'll look at that right there in a little bit. Stereochemistry is very important in drugs. Okay, there's a big example of a drug called thalidomide given in the 1950s and early 60s to pregnant women for morning sickness, mainly in Europe. The drug was created. During the creation of the drug, everything was going well. The drug worked. But when they gave the drug and started giving it to patients, they actually gave the wrong stereoisomer. Okay, it was a big screw up. And one stereoisomer was safe, but the other one, which they ended up giving, led to birth defects. And led to babies being born with really no arms, very underdeveloped arms. Called thalidomide babies. The compound was called thalidomide. Another example of stereochemistry being hugely important. A little flow chart here. Stereochemistry or stereoisomers. Okay, what are isomers? Have the same formula. They're two different types. Constitutional, we've already seen that. They have different what? Different connectivity. And thus they'll have different name. Okay, different name. Stereoisomers have the same connectivity. They only differ in the 3D arrangement. Stereoisomers have the same exact name. They only differ by some type of stereochemical descriptor that you have to put in front of that name, like cis or trans. Or we'll learn others, erythrothrio, RS, D or L, some type of stereochemical descriptor. There's two types of stereoisomers. Enantiomers are mirror images. Mirror images that are different. Because if they were the same, they wouldn't be stereoisomers. They'd be the same thing. Mirror images. If they're not mirror images, they're diastereomers. Diastereomers is sort of a default. You first say, are they mirror images? If not, then they're diastereomers. As long as they're stereoisomers. Okay, there's other things here. Let's start by showing the R, it's underneath the big paragraph, the R and S enantiomers of 1-bromo, 1-chloroethane. The molecule I'm talking about basically I could draw it on the board like this. Everybody agree it's 1-bromo.
Is that in the packet?
I'm sorry?
Is that in the packet? That what you're talking about?
This is in the white.
In the white?
It's in the yellow.
No, I'm sorry, it's in the yellow. In the yellow. It's underneath the big paragraph on the first page. Ethane, right here. 2 carbons, ethane. That's 1 carbon, that's 2. 1-bromo, 1-chloroethane, yeah? Okay? This carbon here also has an H. We could draw that there. Okay? What we have right here is a carbon that has 4 different things attached. Okay? We're going to call this a chiral carbon. Or also we'll call it a stereogenic center. Stereogenic, it gives rise to stereochemistry. An alkene is a stereogenic site or a stereogenic center. We can show this compound 2 different ways. This is tetrahedral. I don't have the tetrahedral shown here. I can show it with chlorine there, boom, boom. Okay, tetrahedral, 2 in the plane, 1 forward, 1 back. I'm going to draw the H back and the bromine forward. All right. I'm not going to draw the mirror image of that. If this was looking in the mirror, pretend it's looking in the mirror, what's it going to see? It's going to see, hopefully it'll look like this. Does that look like if it looked in the mirror to see that? I think that's right. Okay. H back, VR forward. Over there, there'd be an H back and a VR forward looking back at me. This methyl is going sort of away from the mirror, so over here you'd have a methyl going away from here. Hopefully you see that. Okay, are these the same or different? Very different. Because of what? Same or different? Okay, let's see if we can have some paper clips. 2 paper clips here. This paper clip looks in the mirror What does it see? Does it see that, looking back at it? If that looks in the mirror, does it see that, looking back at it like that? Everybody agree?
Yes.
Okay, same or different? Same. That's the same thing. Right? Same thing, right? Okay? Same or different there?
Same.
Those are different. Those are different. Why are those different but these the same?
This is real life.
Do what?
Those are two H's on that.
Here's why. Because if something has a plane of symmetry, does this thing have a plane of symmetry? I cut right through it. Okay? This half is the same as that half. If something has a plane of symmetry, then the mirror image is going to be the same thing. Okay? That's it. Did y'all know that? All right. Does this have a plane of symmetry?
No.
Let's make the molecule. I'm going to have to make the H a color. Let's make it gray.
Blue.
Chlorine green. Is it here? Chlorine green, bromine, let's make red. H going back. See, these two are really sort of eclipsing each other if you're looking right through here. I just do it sort of up and down. Methyl coming this way, methyl black. Okay, that's that. Okay. Let's make the what lines up to be the mirror image. I need a red, a gray, and a green. Red, gray, and a green. Chlorine up. Yes. Bromine red coming forward, is that right? H is gray going back, is that that? Here we go. If this looks in the mirror, does it see that? Does that look like it's looking in the mirror? Okay, same or different? Well, if they're the same, you can stack them on each other. All right, I can't stack this, but basically I can. They'll stack like saucers if they're the same. That's called superimposable. Will these stack on each other? No. I mean, can I just stack them?
Maybe.
The red and green line up, but the black and gray don't. Well, we can make the black and gray line up by doing this. Now everything lines up, right? Oh no. We can never stack these up just like that. If they were the same, we should be able to just stack them and superimpose them. It won't do it. Basically, that tells you they're not the same. What do we have here? We have mirror images. Everybody agree? Yes. Mirror images that are not the same. What do we call these? Enantiomers. That's a chemical word for it. Mirror images that are not the same, enantiomers. Why is a mirror image not the same?
There's no plane of symmetry.
Because there's no what? Because there's no plane of symmetry. See, this thing has a plane of symmetry. The mirror image was the same. You see a plane of symmetry here. Can I slice right through here? If I slice right through there, I go right, I'm slicing a chlorine and bromine, but on this side I have a methyl, on this side I have an H. So I can't do that. How about here? I can slice right through a methyl and an H, but I'll have bromine on one side and chlorine on the other. There's no plane of symmetry. It's all because of this guy right here, that chiral carbon. A chiral carbon, it's a stereogenic center. Because of that, it gives rise to stereochemistry. We also call this an asymmetric, however you spell that, site. Or center. It's a site of asymmetry. Your chiral carbons are your most common sites of asymmetry. Here's the take home. If a molecule has just one chiral carbon, the molecule will not have a plane of symmetry. Game over. And thus, the mirror image is different. These being mirror images is a lot like, or just like this. What's a mirror image of this? That. This looks in the mirror, it sees that, right? Okay? Are these the same? No, this one fits in the right glove, this one does not. Mirror images that are not the same. These are enantiomers in chemical speak. Why? Because there's no plane of symmetry. I cannot slice right through my hand and get a plane. Here, I got thumb on one side, no thumb on the other. If I try to slice through here, I got top of hand on one side, palm of hand on the other. If this was like a slice of bread with the same on both sides, I could slice through it. Take home is you look for planes of symmetry. Okay? These are called enantiomers. Now, are these isomers? Sure, they have the same connectivity. They're both one bromo, one chloroethane. So they're stereoisomers. What type? Mirror images that are different. Flow chart tells us that's enantiomers. How do we name these? Before we do that, question?
So if there's just one plane of symmetry that we can find, then this will no longer apply. Just one plane.
So you can find a plane of symmetry, game over. They're not. It's the same thing. Mirror image is the same thing. But if you have one chiral carbon, you're not going to find a plane of symmetry.
Okay.
You can't. What was the other one?
If we had two chlorine rather than...
Okay, yeah, let's do that. Before we move on, what do we want to call these? I call this a right hand and left hand. In chemical speak, we don't use right and left. What terms do we use here? For individual carbons, we use R and S. For molecules as a whole, we do something else, and we'll get there. Let's determine RS here. Basically, we're determining the configuration around our chiral carbon. How are these groups put around the chiral carbon? We do this a lot like we do E and Z. We assign priorities based on atomic number of things. There's 4 things on this carbon. What's the highest in terms of priority? Bromine, 1. What's next? Chlorine. 2. Then the carbon, 3. H would be 4. I'm not going to do that. 1, 2, 3. Now with the lowest priority group in the back, do we have lowest priority group in the back?
Yes.
Lowest group back. Check. We look at 1, 2, and 3. Is 1, 2, and 3, look at it. Is it clockwise on your paper or board or counterclockwise? 1, 2, 3. It's counterclockwise. That will be what? S. S is counterclockwise. Let's look at the other one. Priorities. 1, 2, 3. Where's the 4 group? Is it going back? Yes. Okay, with the low priority group going back, is this clockwise or counter? 1, 2, 3. What do we have? Clockwise, we call this configuration R. S configuration, R configuration. Now we have a stereochemical descriptor. And we can call this compound here S1 bromo 1 chloro ethane, right? What do you want to call this one? R. Same name. Same exact name, just have a different stereochemical descriptor. And we did just use the orientation around the carbon. Okay. Now, what about enantiomers of 1,2-dibromoethane? I'm going to do this without erasing. I know you can't erase easy, but I don't want to. I want to try to do this quickly. If both of these were bromines, are these different? Let's see. What was bromine? Green. Let's put 2 greens. And so, bromine up, coming out at you, methyl coming this way. And if it looked in the mirror, it should see no. There you go. Looked in the mirror, it would see that, right? Okay, are these mirror images? Yes. Everything's got a mirror image, except vampires. All right? Yes, that's a mirror image. Question though is it different? No. It's the same. Why is it not different? Well, can you superimpose them? Green and gray line up, but those don't. Or do they? How about that trick? You see how they stack on each other? Why do they stack on each other? Because they're the same thing. Why are they the same thing? Because now we have a plane of symmetry. See, I can cut right through here. I got a bromine on one side and a bromine on the other, and I'm a half a methyl on one, a half a methyl. I got a slice right through there. This has a plane of symmetry now. Thus, we know the mirror image is going to be the same thing, just like the paperclip, right? So there, how many compounds on the board there? One. That's one compound. There's no stereochemical descriptor that goes in front of that. That's 1,1-dibromoethane. That's it. Okay? Go back to the chlorines. Those were enantiomers. Enantiomers have identical physical properties. I mean, they have the same connectivity. They're just mirror images. You would expect them to have quite similar physical properties. They have the same melting point, same boiling point, same dipole moment, same density, etc.
Experimentally, how do you tell them apart?
Thank you. That would be number one. There's two things that differ, and there's two ways to study them, mainly. Number one is what we're doing in lab this week. Enantiomers rotate plane polarized light in equal but opposite directions. Sort of a quirk of nature. Somebody discovered this a long time ago, perhaps Louis Pasteur. The one that rotates light to the right is called the dextrorotatory isomer. Somebody got this in front of them? Yeah, I don't need to show it on the overhead here. I'm just sort of going through here. To the right. This is to your right. You're the viewer. Okay? To your right, you're going to be doing dextrorotatory. D. The right is also the positive direction. If it rotates light to the left, it's called levorotatory. Levo starts with L, left is L. That's how I remember that. Levo, left. Importantly, let's go back to the chlorines here. Was it the top chlorine? Okay. R and S has nothing to do with D and L. What do we know about these two? These are bacterial enantiomers. One of these rotates light to the left, and one of these rotates PP light to the right. Which is which?
You don't know.
We don't know. It has nothing to do with R and S. But there's some terminology. This is often called a DL pair. Because one is D and one's L. You don't have to know which is which to call it a DL pair, do you? Okay? So that's terminology. Enantiomers are often called DL pairs because one rotates one way and one the other. Has nothing to do with R and S though. D and L comes from an experiment in the lab. R and S is sort of man-made convention for assigning how it's oriented. We'll talk more about D and L, of course. Number two is they interact with chiral objects differently. You knew this when you were 2 years old. Because when you were 2 years old, you tried to put your right hand into the left glove, it didn't fit. Your right hand is chiral, because the mirror image is different. But see, gloves are also chiral. And this will only interact This interacts with gloves differently, right? That's what number 2 means. Now, more scientifically, a chiral drug will interact with a chiral receptor differently. One enantiomer of the drug may interact with the chiral receptor where the other one will not. Analogous to hands going into a glove. And that's probably why that thalidomide drug became toxic, because one, the bad enantiomer probably went and did something when it wasn't supposed to be doing it. It's like it stuck its hand into the glove when it wasn't supposed to be a good match. So, number 1 is something relevant to the class. Number 2 is something more when you get out and you talk about receptors and stuff. Let's look at enantiomers of 2-butanol. While I'm erasing, let's see if there's any questions.
What is plain polarized light?
Well, light has, you know, wave propagation in all directions. Magnetic, electrical waves. Some of you guys that had physics more recently can talk this language better than I can, but light made up both electrical and magnetic wave and it's perpendicular. But those waves are also all sorts of planes. I mean, the wave can be like this or it can be like that. PP light has just one plane of those wavelengths. And it turns out that that type of light can be rotated by an enantiomer. Basically, that plane gets rotated. If you've got all types of planes like you have from regular light, you can't tell what's rotated because it's just a wash. Let's see if we can draw enantiomers of 2-butanol. Are there really enantiomers? 2-butanol. We really didn't do nomenclature of alcohols, but butanol, sounds like it's butane with an OH. Where do you think the OH is at? Which carbon? 2. Okay? So I'm going to put it here. I can draw that like that, but that's tetrahedral. And how many different things are on this carbon? 4. Methyl, oh, there's an undrawn H. 4 different things on a tetrahedral carbon, that's a chiral carbon. It's an asymmetric carbon. No symmetry there. That's what we've done. No symmetry there. Because there's no symmetry there, there's actually no symmetry in the whole molecule. That ruins it for the whole molecule. So the whole molecule is not symmetric. How can we show these? Well, we can show the tetrahedral nature. I can put the OH forward. Let's do it this way, mirror image. What would the mirror image look like? I mean, the H might be there, that's irrelevant. Does that look like mirror images? Yeah. Let's do R or S here. There's 4 different things here. That's high priority? Okay. Carbon with another carbon or carbon with just H's? What's the 4th group? The H. And the H is how? Back. It's back because the tetrahedral has 2 in the plane, 1 forward, the other thing is back. The H is back. Is this R or S? R. 1, 2, 3. Clockwise is R. Do you expect the mirror image to be same or different? Different. We've already said if you got 1 chiral carbon, it's not going to be, there's no plane of symmetry here. Okay, we can make a model, make your models. If you have 1 chiral carbon, that ruins the whole symmetry. That means the mirror image is different. Different molecule. Now, when R looks in the mirror, what does it see? If an R configuration looks in the mirror, what does it see? Yes. Okay? be my mirror. Okay, I'm holding up my right hand. Which hand are you holding up? Left. You see how it switches? Now I'm holding up my left, and you're holding up your... When the left hand looks in the mirror, it sees the right hand, okay? When R looks in the mirror, it sees S. That's R. Oh, there's S. Assign priorities. 1, 2, 3. O, right? Which way are we going? Counterclockwise, so it's S. It's like a right and left hand. Now there's another way to show S without showing what looks like a mirror image. What if I had drawn this with this going back? That's one of those over there. Which one is this? Which one is this? Somebody?
Oh, yeah.
I hear an S.
Yes. Yes.
How do you know it's S, T?
You flip it like that. Your hand.
Okay. This is indeed S. Okay. These two are the same thing. There's two ways to get to the enantiomer. You can draw what looks like a mirror image. That'll be your enantiomer. You can also just switch your bolds to dashes. As long as you keep the backbone the same. Okay? Let's determine, is this R or S? By our convention. That's 1. That's 2. That's 3. What do we have here? Clockwise. Which is, yes, but low priority group has to be where? When we do this. Is the low priority group back?
No.
LP group is forward. Isn't the H there forward? If it's forward, you just switch what you get with your clockwise. It looks, we got clockwise on the board because it's forward. Switch to S. Okay? Basically, here's the molecule with the OH forward. All I've done is brought it over here, and now it's back. But see, I'm rotating this carbon when it turns, it goes over here. And so it's now here, but it's also back. Okay? You need to make models, you need to just see, all I've done is just rotate. I told you, there's two different ways to get to an answer. Draw what looks like mirror image, or just switch everything. Remember. Okay, let's do it here. All right, you do this. I got right hand forward, you got left hand forward. I got left foot forward, you have right foot. See, everything's switched. And if you look in the mirror, everything gets switched. So if we had multiples, you would change everything. Now, let me give you some other information here. The S, this is a DL pair. I know from experiment that this one, alpha, which is the specific rotation, this is your rotation of the PP light, equals 13.5 degrees. Specific rotation of PP light. You'll learn in lab, the specific rotation is based on denominators of 1 in terms of concentration and path length. If that's plus 13.5, this one is negative. Because as we saw up in 1, they rotate light equal but opposite directions. Since this is negative, this is which enantiomer in terms of DL? L. Okay? Because negative is LIVO. Since this is positive, this is D. Okay? I'll just put L. This is actually another stereochemical descriptor. You could call this R2-butanol, or we can now call it L2-butanol. Either one works. That comes from experiment, though. That's experimental data there. Okay? That's just drawing down the board. It's a DL pair where actually that one's D and this is L. But again, D does not go with S. Sometimes you may have D and R. Okay, we're basically out of time and we're basically where we're going to be doing in the lab. The next section is optical activity. Okay, we're going to talk more about the rotation, how to determine when you have like 75% of one enantiomer, 25% of the other. Because this here is only when you have 100%. We'll be doing this in lab this week. We'll pick up here on Thursday. Please read ahead. Unfortunately, we're out of time. See you Thursday, guys. Please be reading ahead. Please be trying to do the warm-up questions. Warm-up questions. Tuesday through Friday, I believe. Are we going there now?